Hello and welcome to this video on Le Chatelier's principle. This could be useful for AQA GCSE, any GCSE syllabus in fact, and actually in year 12 in the rates module of OCR A, looking at Le Chatelier's principle there. So Le Chatelier's principle very simply states that the position of equilibrium will react to oppose a change made. And we study three changes, which is the effect of concentration, effect of temperature, and the effect of pressure. And I'm going to attempt to demonstrate all three here. So let me have a look. In this example, I'm going to use the Haber process, which is probably one of the most commonly studied equilibriums. So this is for making ammonia, and we've got nitrogen here in the gas phase, hydrogen in the gas phase, and we're making ammonia actually in these conditions in the gas phase. And this equilibrium is shifted by a number of processes, and in industry they actually don't use the optimal processes for reasons I'll explain later. So let's first have a think about what is the effect of concentration on an equilibrium. So obviously Le Chatelier's principle states that a system will oppose the change made. So if we focus on the ammonia, if I added more ammonia, then the position of equilibrium would shift to the left because it would oppose that increase in concentration, remove some of the ammonia and convert it back to nitrogen and hydrogen. If I remove the ammonia from the equilibrium, then the position of equilibrium will shift to the right. In other words, for A-level students, my Kc value would go well above 1. And the system would make more ammonia to compensate for the ammonia that I had removed. The second effect we can look at is temperature. And bearing in mind again that it will shift to oppose the change made. Now this forward reaction is exothermic and this backward reaction is endothermic. Now if I increase temperature, if I increase it, I will shift in the endo direction. The endothermic direction. So if I decrease the temperature in this reaction, it will go in the exothermic direction. So actually a low temperature is very favourable in the Haber process. However, if I do the reaction at a low temperature, I won't have the frequent successful collisions initially in the reaction between nitrogen and hydrogen. So a compromise is made actually at 450 degrees, quite a high temperature, that even though this isn't favoured by equilibrium, it is favoured by basic reaction rate, and it's much better for the reaction to go faster and us to take out the ammonia and then allow Le Chatelier's principle to move with concentration. The third way in which you can affect an equilibrium is pressure. Obviously this is in the gas phase. Now the rule is that with higher pressure, equilibrium shifts to the side with less moles of gas. Quite a lot to write, not too much to remember. So basically, as you squeeze something, we say 1 mole of gas occupies 24 dm cubed at room temperature and pressure. So obviously more moles of gas is more volume. If I squeeze something, it will try to counteract that change, following what Le Chatelier said. Okay, it will counteract that change and make itself smaller by becoming less moles of gas. So if we look at this equilibrium here, I've got 1 mole of gas with the nitrogen, plus 3 for the hydrogen. So on this side, I have 4 moles of gas. And on this side, I just have 2 moles from the ammonia. So if I squeeze this, if I put it under high pressure, then my position of equilibrium will shift to the side with least moles, and I will make more of the ammonia. So why don't they just max out the pressure? It's actually done at about 300 atmospheres, but obviously with higher pressure you need more expensive equipment. So there is that cost kind of influence to consider as well. The fourth thing that's worth talking about here is the effect of a catalyst, and this one I'm going to end on. A catalyst doesn't influence the position of equilibrium at all. All it does is speed up the attainment of equilibrium, so it will get to its equilibrium position much faster with a catalyst present. So I hope you've enjoyed this video. Please like, comment and subscribe. I'll see you in the next one.